Hello class, today we are going to look at inductive versus deductive reasoning. But before we get into that, I would like for you to pause the video and take this really quick true-false test. Consider each of these statements, determine is it true, if it's false, and if it's false, give a counter example. Give an example that shows that this is false. All right? So pause the video and come back and see how you did. All right, you're back. Let's see how you did. And here are the answers. All right, so we have A times B plus C equals A times B plus A times C. This is the distributive property, right? You just multiply it in there, and that's true. Sure. Birds fly. That is a false statement. Penguins are birds. Penguins don't fly. And the statement says that birds fly and penguins don't. So there you go. Deer have antlers. Fawns are deer. Fawns don't have antlers. Neither do does. So, no good. Texas is in North America. Yep, only place Texas is. Texas is North America. A rectangle has 4 right angles. That is the definition of rectangle. Rectangle. Rect means 4. Right and angles. Right angles. Fish live in lake and streams, which is false because Nemo lives in the ocean and he's a fish. Athletes play football, also false, because some of them play baseball or something else, soccer. Geometry is a mathematics course. Yes, all geometry is mathematics, so that one is true. Humans are insects. No humans are insects. All right. And Austin, Texas is the capital of Texas, and that is also true. That is the only capital of Texas. So as you see here, in order for a statement to be false, all we really have to do is find one statement, one case in which it is false. That's it. It only takes one. All right, so now let's get into inductive reasoning versus deductive reasoning. I just wanted to hit on that really quick. So let's just start with this conjecture. All right, when we're talking about logic and we're talking about things, we're going to make conjectures, okay? This is just a statement that has not been proven, but it is based on some observations. This is not just some random guess. All right, we've seen this in the past, and this seems to work, so we're going to make a conjecture based on it. So really quickly, we are going to make a conjecture about the sum of 2 negative integers. So let's just pick some negative integers. Let's see, how about -2 plus -3, and we end up with -5. Okay. Let's pick some other ones. Let's say -17 plus -21. Let's see, 1 plus 7 is 8. And so that would be -38. So we've got some examples here, right? Because we made some observations. Now we need to make a conjecture based on this. Well, looking at this, it looks like the sum is always going to be negative. Sure, always negative. Always negative. It does say to test it, so let's test. Let's pick some other numbers. How about -15 plus -5 equals -20? All right, so there it is. Looks like we're good. The product of 3 consecutive non-zero integers. For those of you who do not remember, consecutive means one right after the other. So let's see here, non-zero integers. So how about 1 times 2 times 3? 1 times 2 is 2, times 3 is 6. Now we've got to let's make more than one observation here. So let's go with 4 times 5 times 6. All right, let's see here. 4 times 5 is 20. 20 times 6 is 120. Okay, so let's make a conjecture here. Well, let's see. They are both even. Both even. Let's go with that. We'll say it's always even. Always even. So let's try something else to see. It doesn't say it has to be positive, does it? It says it can't be 0. So let's try throw some negatives in there, because if anything's going to mess stuff up, it's going to be negatives. So let's try -2 times -3 times -4. Those are consecutive. Let's see here. So we have a negative times a negative is positive times another negative is going to be negative. And 2 times 3 is 6, and 6 times 4 is 24, which is still even. So we're good. We're good. All right. So there we go. Those are conjectures. Got to make an observation first. Okay. So now it comes to counterexamples. This is a specific case for which the conjecture is false. Notice that a counterexample is specific. You can't just say, yeah, well, sometimes it doesn't work. Okay, yeah, when? Prove it, buddy. All right. You got to have a specific case when it doesn't work. All right. And in order for a statement to be false, you only have to have one counterexample. If a statement is 99% true, then that statement is 100% false. All right. So here we go. We want to find a counterexample for this conjecture. The value of x squared is always greater than the value of x. Okay, so there's two things. When you're looking for a counterexample, there's two things that are going to probably be it every time. Well, if there is a counterexample, it's usually going to be one of these two things. Number one, you want to test negative numbers. Test negatives. Test negative. I can't write. Negatives. That's going to throw it off most often. Negatives. The thing that will throw it off other than negatives will be to test fractions. All right. Test fractions. So let's try negative numbers. Let's see if that will throw this off. Let's see here. So x squared is always going to be bigger than x. So let's try negative 2. Why not? Negative 2 squared equals, well, negative times negative is positive. That's positive 4. So that's no good. Not what we're looking for, because that proves that it's true, right? So let's try fraction. Let's try fraction. Let's try, how about 1/2 squared? Well, let's see here. 1/2 times 1/2. Well, 1 times 1 is 1, and 2 times 2 is 4. Hey, there we go. 1/2 squared is 1/4, and is 1/4 more than 1/2? No, it is not. So here we go. This does not work, and so we've proven that this statement is false. All right. Another number that also does tend to throw things off a lot are 1 and 0. All right. Because, for example, if I plug 0 in here, or 1, either one, 0 squared is 0, and 0 is not more than 0. It's equal to 0. Same thing is true with 1. 1 squared is 1, which is not more than 1. All right. So you can also test 0 and 1. Those are other things that will a lot of times screw it up where everything else works. All right. I would start with negatives. Negatives work the most often. All right. So counterexamples, you only need one. One counterexample is enough to prove the entire statement false. Okay, next we have inductive reasoning. Inductive reasoning, this is what you use to find a pattern in specific cases, okay? So we looked at these specific cases up here, and we said, well, it looks like this should be true, and so here's we go, here's our pattern, here's what we're going to go with, all right? And that is what inductive reasoning is for. You take specific things you know to be true, and then you make a generalized assumption based off of that, all right? So this is kind of like when you're using your gut, you know, I just get this feeling, okay? Intuition is inductive reasoning. It takes all these little things you're not always even aware of and puts it together and makes a conclusion, all right? And this is what you do when you find patterns. Anytime you're finding patterns, you are looking at inductive reasoning, all right? So let's see here. Let's find some patterns here. So we have 20, 19, 17, 14, 10, 27. Okay, let's see. Well, let's see what we'll change by. Let's see. We're going down to... Move those out of the way. There we go. All right. So let's see. That one is going to go down 1. That goes down 2. That goes down 3. Down 4. So it's decreasing by 1 more than the previous, right? So describe the pattern. We will say decreases by 1 more. one more. Then, right, give the next two numbers or letters. So let's see. So the next one would go down 5. So 10 minus 5. The next one would be 5. And then after 5, we would go down 6. And so that would make it -1. All right? So not too bad. See if you can pause the video, come up with a pattern here. Again, this is inductive reasoning. And it's because we're just making, kind of going on the instinct. We don't know for certain, but it looks like it should work. All right. And so you'll see we have C, D, E, F, G, H, I, J, K. We are skipping a letter. Skip a letter. That is awful handwriting. That's a little bit better. Skip a letter. So after J, we'll have K, L. We're skipping L, so we'll have M, N, and then we'll skip N. And so we'll have O. That's all. All right. Inductive reasoning. All right. These are things you got a good idea, but you don't know. You know, these are things like, well, you know, every week on Friday for the past 2 months, we have had hamburgers in the cafeteria, so odds are this week on Friday we will also have hamburgers in the cafeteria. So some specific cases making a generalized assumption. All right? Deductive reasoning, on the other hand, goes differently. Deductive reasoning uses facts, definitions, accepted properties, laws of logic, things that always work on the big, broad spectrum, and applies them to specific cases. Okay? So, let's go ahead and let's fill this out here. Inductive reasoning. Inductive reasoning is based on patterns. All right? It is based on observation. Patterns, observations, like we did over here to make the conjectures. Observations. It is based on past experience, like my cafeteria example. All right, this is what I've seen in the past, so this is what I'm going to conclude about the future. All right. Deductive reasoning is not based on patterns. It's not based on things I've seen in the past. It is based on the rules. It is based on facts. All right, for those older to remember, Joe Friday, just the facts, ma'am, just the facts. All right. It is based on fact. It is based on rules. These are the rules. This works every time, so it must also work in this time. It is based on definitions. All right. And it is based on properties. All right. Inductive moves from specific cases. All right. Last Friday, the Friday before that, the Friday before that. Specific cases to a general rule. So since it worked every other Friday, it must also work, you know, it started to happen these last 5 times, so it's going to happen every time. General rule. General rule. All right. Deductive reasoning goes the opposite direction. I have a general rule. This always works. These are the rules. General rule. And so since it works every time, it is going to work this time too. General rule to specific case. To specific case. All right. Okay. Inductive reasoning I use to make a conjecture. Make a conjecture. Deductive reasoning is used to test the conjecture. Test a conjecture. All right. Inductive reasoning, if your premises are correct, your observations are correct, your conclusions are usually true. usually true. You know, it is true that the last 5 weeks on Friday we had banana pudding offered in the cafeteria. So I am going to conclude that we will always have banana pudding offered on Fridays. Does that mean that we have to? No. Maybe whoever makes the banana pudding was sick that day, and so they didn't make banana pudding. Maybe there's Ebola in the bananas, and so there's no banana puddings. I don't know. Whatever. Usually true, but not always. Deductive reasoning, on the other hand, if your premise and you are properly applying the facts and the definitions, your conclusions will always be true. Always true. All right. To put this in pop culture terms, inductive reasoning is Dr. House, deductive reasoning is Sherlock Holmes. All right. Now, we will be mostly using deductive reasoning. We're going to talk about 2 laws of deductive reasoning. The first one is the law of detachment. And what the law of detachment says is that if the statement, if P, then Q, is a true statement, if hypothesis, then conclusion, if that is a true statement, and it is true, P is true, then Q must also be true. All right? So let's take a look, see how this actually works, all right? Because that makes more sense. We actually see them. So what we have here, if a triangle has equal length sides, then each interior measure is 60 degrees, okay? Triangle ABC has equal length sides. So let's see here. We said if P, then Q. So let's take a look. Let's put this in if-then form. So if triangle has equal length sides, so there's our hypothesis, and this is our conclusion. Each interior angle measure is 60 degrees. Okay. Triangle ABC has equal length sides, right? So that's our P. P is true. The hypothesis is true. So we're good. All right. This is P. This is Q. And here I am saying that P is true for this specific triangle. All right. And if P is true for this specific triangle, then Q must also be true for that specific triangle. And so I can conclude that triangle ABC has interior angles that measure 60 degrees. Well, measuring would be better grammar. Measuring 60 degrees. So let's take a look at statement 2 here. Let's see. If a quadrilateral is a rhombus, then it has 2 pairs of opposite sides that are parallel. So hypothesis, a quadrilateral is a rhombus. That is our P. Then, conclusion, it has 2 pairs of opposite sides that are parallel. Right? Right. So that is Q. And let's check it for this specific quadrilateral PQRS. Has 2 pairs of opposite sides that are parallel. So does that match up with P or Q? Well, that matches up with Q. So let's see, it has 2 pairs of opposite sides that are parallel. Now, if you'll notice, the law of detachment says that if P is true for your specific case, then Q must be true. Does it say that if your conclusion is true, then your hypothesis is true? No, it doesn't. Because here's the thing. If you have 2 pairs of opposite sides that are parallel, that could be a rectangle, which is not a rhombus, right? So for this, we don't know. Quadrilateral PQRS might be a rhombus. It might not be. There is no conclusion possible because we don't know. The hypothesis is not true, so we can make no conclusions about no assumptions about the conclusion. We don't know. All right, this brings us to the law of syllogism. And what the law of syllogism says is that if P implies Q is true, and if Q implies R is true, then if P is true, then R is true. Okay? A little weird, but let's take a look at this. Okay. So what this is saying, if the conclusion of one statement and the hypothesis of the other statement are the same, and both of these are true statements, then we can go straight from the hypothesis of one to the conclusion of the other. So let's take a look here. So it's here. If it does not rain, then I will walk to school. All right? So let's see. Hypothesis. It does not rain. Then I will walk to school. Conclusion. I will walk to school. So here. If I walk to school, then I will wear my walking shoes. Let's see. Does this match either of my first two statements? Yeah, the conclusion up here. I will walk to school. Does this one match either of those statements? No. So that's a totally new thing. We will call that one R. All right. So what we have, let's move that over. Okay. No, that's not over. Okay, so we have, call this P. Here's Q. Here's Q. And then we have a new thing, which we will call R. Right there. Okay. So the first statement, P, then Q. If P, then Q. The next statement, you see we've got Q. Same thing we had before, right? Let me get something to hold that down. There we go. A little bit. So Q will line it up under the Q. Q, if Q, then R. And since that works, I can go straight, since these two are the same, they match up, then I can go straight from P to R. So I can say if P, then R. So let's write this as one statement. If it does not rain, then I will wear my walking shoes. All right? So if this statement is true, and this statement is true, and since they have the same, the conclusion here is the hypothesis there, then I can put it all together as one statement. All right? So let's take a look at this next one. If a figure is a rectangle, then all interior angles are right angles. So let's see. If a figure is a rectangle, we'll have that one here. Then all interior angles are right angles. So here's my conclusion. So I have if P, then Q. Right? Okay. Next statement. If a figure is a square, have I had that statement yet? I have not had that clause yet, so that is a new clause. That is R. Then all interior angles are right angles. So we can do that. All interior angles are right angles. I already had that before. That's Q again. Okay, so now let's put this in like so. I have R, then Q. So looking at this, notice my Q's line up, but it doesn't flow, right? It doesn't go from one to the other, does it? These are both conclusions. And since these are both conclusions, can I put P with R? No. It has to be like this. One's a conclusion, one's in the hypothesis position. If it's not, then the law of syllogism does not apply here, and so there is no conclusion possible. Very, very important that it match this pattern, okay? Now, it could be R, then Q, and then Q, then P. That's fine. But it has to match this pattern where the two that match up, one is a hypothesis, and one is the conclusion, all right? So it has to be in different spots on the two different statements, all right? So, in conclusion, where to go? Conjecture, an unproven statement. You see something happen a few times, and you make a guess about what's going to happen next based on those statements. And we use inductive reasoning to do that. All right? Deductive reasoning is used to test the conjecture. Let's follow the rules. Let's see. Can we find a specific case where it doesn't work? This is deductive reasoning, where we test it, follow the rules. See, does this work every time? All right. Deductive reasoning is what we will use the most, all right, because it's going to use facts, laws, definitions and properties, theorems, things like that. All right. Law of detachment. Okay, if P then Q works for every case, then if P is true for a specific case, then Q will also be true for that specific case. All right. Law of Syllogism. If P then Q, and if Q then R, then if P then R. Okay, and that one's a little bit weird, a little bit tricky, but not too bad. Hopefully y'all found this useful, and I'll see you in the next video.